Hello, my name is Vivek Bhatia and this is the final presentation for the term project for the course CSCI E-93 Computer Architecture for fall 2017. As part of this presentation, I'm going to describe a little bit about my instruction set architecture, which is called Visa 16. It mimics the MIPS 32-bit computer architecture. I'm going to talk a little bit about the reference data for the ISA, the block diagram for the CPU, and the special feature which I've implemented, which is the hardware multiplier. I'm also going to describe the assembler and the emulator which supports the instruction set architecture, and finally demonstrate the implementation of the CPU in VHDL with the final term project, which is to multiply two numbers. And I'm also going to demonstrate the performance of the hardware multiplier in real time. We are now looking at the principles of operation document for Visa 16. Visa 16 mimics the MIPS 32-bit architecture for the most part, using a load store architecture for accessing data to and from memory. Similar to MIPS 32, all ALU operations are restricted to registers only, which means that data has to be loaded into registers prior to performing any arithmetic operations. The general word size in Visa 16 is 16-bit. Memory access is also limited to 16-bit only. No half-word or byte-size access is supported. In addition, Visa 16 supports 16-bit general-purpose registers for instruction execution, in addition to 4 special-purpose registers, which are the program counter, the instruction registers, and a high and low register for storing the multiplication product. There are 16 general-purpose registers, starting from 0 through 15, and each of them have a specific name, which is mentioned in the reference data, which is what an assembler would use in any of the assembly programs. The basic instruction formats supported in Visa 16 are the R-type instructions, the I-type instructions, and the J-type instructions. For the R-type instructions, we support the 2-operand instruction, which has an opcode, a destination register, and a source registers, and the output from the ALU is written back into the destination register. We have 1 operand, which does the same thing but only operates on a single register. The I-type is similar to the R-type, except that it does not do any ALU functionality. The bits for the ALU function are instead used by the offset or the immediate fields. And similarly, the J-type instructions only supports an opcode and an immediate. We support close to 21 instructions in 21 separate instructions in the Visa 16 architecture, ranging from ALU operations to loading and storing words on memory, jumping to specific address, calling specific address loaded in registers, loading immediate values in registers, branching on equality, branching not on equality, and moving the value from high and low registers into the general purpose array. In addition, we support 2 instructions which are as part of the pseudo instruction set, which is the move instruction and the LA instruction. Next, we look at the block diagram for Visa 16, which resembles mostly the MIPS 32-bit architecture, supporting a program counter, a memory subsystem, a register array, and ALU. In addition, the special feature for Visa 16 is the hardware multiplier, which is outside of the ALU. The results from the multiplier are written back into the high and low registers, which can be fed into the general purpose registers using the move high or MF low instructions. Next, we move on to the assembler for Visa 16. The assembler for Visa 16 supports assembly of programs written using instructions in Visa 16 instruction set architecture. It's a simple 2-pass assembler. The inputs to the assembler can be any one of the following, including comments, which are any lines preceded by the hash symbol, instructions, which are comma-separated values of any of the opcodes followed by the register names, and assembler directives in the form of a text segment, data segment, words reserved in memory, null terminated ASCII strings, and uninitialized memory in the form of a dot space directive. In addition, the assembler also supports labels for forward referencing, and any white spaces and comments in the assembly file are ignored from processing. To demonstrate the assembler, we're gonna assemble one of the sample programs written for this course, which is the program to multiply 2 numbers, taking inputs from the user and outputting the product to the serial port. So I already have a compiled version of the assembler. And if we run the executable without any arguments, it shows that it requires the first argument is the assembly program, and the second argument is the output file to write to. So if we load up that file, as you can see over here, I passed the input file, the assembly file as the input to the assembler, and it provided a success message at the end, which means the assembly was successful. It also shows some debug messages in to std out, which can be used to find errors if there were any during the assembly. And if we look at the output of the MIF file, we have the header segment, and then any comments in the assembly file are written directly as is to the output file, along with the address of the memory and the data to be written to memory. I also output the exact line from the assembly program as a comment for debugging purposes. Next up, we move to the emulator for Visa 16. For demonstration, we're going to load the MIF file which we generated using the assembler before into the emulator. So I already have a precompiled version of the emulator over here, and if you use it without any arguments, it shows that it requires a MIF file for emulation. We're going to pass the file which we generated moments ago. And as you can see, the emulator's initialization succeeded, and it requires a user input to proceed. I also want to point out that for debugging purposes, I output the exact value of the register array and the memory subsystem for as part of the emulation. We can step through each instruction. As you can see, the output of the register array is updated over here, and the memory output is also updated. If we run through the actual program, it runs through the program as is. As you can see, the execution is pretty slow because there's a large amount of input-output being performed over here. But you can use that to debug programs written in Visa 16 assembly language. Next, we're going to demonstrate the assembly program which we just ran in the emulator on the E-270 board. So I've already compiled the program in Quartus and deployed it on the FPGA, and I've loaded the assembly program which we just looked at onto the memory subsystem. Before we begin demonstration, I would like to point out the debugging outputs available on the E-270 board. I do tap into some of the buses on the CPU to output to the hexadecimal display. We can look at the MIF number being executed, the actual number of the MIF line being executed, the output of the program counter, the jump addresses, and the complete register array. In addition, I also output control signals from the sequencer onto some of the LEDs. So I have a simultaneous screencast of the FPGA being displayed over here, and we're going to run the final program in just a moment. And I have a serial port set up, and as you can see, the clock is now suspended. And if we run through the clock, you can see over here the output is being delivered to RS-232. You can choose two numbers. 3 and 3 is 9. You can choose negative numbers. As you can see, the instructions are being performed over here. It also supports instructions with 0 and very large number. I would also like to point out a little bit about the debugging output available on the D270 board. Right now, switch 16 is held high, which means the clock is suspended, and as you can see, the output of the instruction register can be seen. We can also look at the output of the program counter, some jump addresses, and the complete output of the register array. We can also step through instructions, through the actual clock cycles, and see the CPU state changing along with the state of all the LEDs. So for the final part of the presentation, I'm going to demonstrate the performance of the hardware multiplier as compared to doing multiplication on software. So I have a program which is already loaded onto the FPGA, which prints out the multiplication table. So if I stop the clock over here, you can see that it runs ranging from the first operand ranging from 0 to 1000, and the second operand ranging from 1 to 9. And you can see the output values being printed over here on console. So if I let it run, it's going to print values up until it reaches 100. In the effort of in the interest of time, it becomes a little difficult to time this operation since there's a lot of output to console. So I'm going to do is run the same program by suppressing the output to RS-232 console. We're going to time first the hardware multiplier first. I'm going to run the same program and we're going to time it. And what we're looking for is the output done over here. Reset the clock, reset FPGA, and 1, 2, 3, go. You're gonna see it done over here at some point, and there it is. So about 8 seconds. And you're gonna run the same program using multiplication and software. Again, suppressing the output. Load the program, and we stop the clock again. See the output, and 1, 2, 3, go. And there it is. So it took about 1 minute and 26 seconds as compared to taking 8 seconds with using just the hardware multiplication. With that, that concludes the final presentation, final part of the presentation. I will take any questions right now. Thank you.